Buenas tardes. Hello. Hello, everybody. Good afternoon. Boa tarde. I am Andrea Coronato. I'm researcher of CADIC CONICET at Ushuaia in Argentina. I am also one of the IAG vice presidents and the Latin American co-opter of IAG. IAG is the International Association of Geomorphologists, as you may know. Together with my colleague from Universidad Federal de Bahia in Brazil, Grace Alves, we are in charge to coordinate this fourth IAG webinar to celebrate the 2024 International Week of Geomorphology for this part of the world, for our Central and South American territories. This is an official activity of IAG, so the presentations and some lectures must be in English. But anyway, we also use Spanish and Portuguese, our local languages, for some lectures, for questions, for comments. So please feel free to participate in any of the three languages. All of them are accepted. Buenas tardes a todos, ahora en español por las dudas. Soy Andrea Coronato, soy investigadora de CONICET en el CADIC, en Ushuaia, y uno de los vicepresidentes de la Asociación Internacional de Geomorfólogos, más conocida como IAG o IAG, y además soy representante para Latinoamérica de esta asociación. Y hoy, junto con Grace Alves, mi compañera de la Universidad Federal de Salvador de Bahía y secretaria de la Unión de Geomorfología de Brasil, estamos encargadas de organizar y de llevar adelante este cuarto webinar para celebrar la Semana Internacional de la Geomorfología del año 2024. Esta es la cuarta oportunidad en que nos reunimos en esta primera semana de marzo para realizar esta actividad. Les decía que como es una actividad oficial de IAG, el idioma oficial es el inglés. Por eso abrimos la reunión hablando en inglés. Pero de todos modos podemos hablar en español, en portugués, y les pedimos a todos que por favor se sientan libres de hacer preguntas, comentarios en cualquiera de los tres idiomas, porque todos son aceptados. Grace?
Boa tarde. Boa tarde a todas e todos. Eu sou a Grace Alves, sou professora na Universidade Federal da Bahia, sou secretária da União de Geomorfologia Brasileira e estou aqui junto com a Andrea Coronato, pesquisadora do CADIC CONICET em Ushuaia, Argentina, também vice-presidente e representante da América Latina no IAG. Nós estamos encarregadas de dar boas-vindas a todos e todas que estão aqui assistindo o quarto webinar para celebrar a Semana Internacional de Geomorfologia. Por esta ser uma atividade do IAG, né, da Associação Internacional de Geomorfologia, nós utilizaremos o inglês em algumas apresentações. Também vamos comentar e perguntar e discutir em espanhol e português, que são as nossas línguas locais. Então, por favor, se sintam à vontade de fazer perguntas em português, em espanhol, em inglês, a que for mais conveniente, que nós iremos repassar para os jovens profissionais de geomorfologia que estão apresentando hoje, para que a gente tenha aí uma rica tarde. Andrea?
6 young geomorphologists from Costa Rica, Brazil, Chile, and Argentina, some of them living abroad or working abroad, are the protagonists of this webinar, in which they will share their results coming from postdoctoral studies or coming from their participation in research projects. We want to deeply thank to all of them. 6 geomorfólogos de Costa Rica, de Brasil, de Chile y de Argentina son los protagonistas del webinar de 2024 y ellos van a compartir con nosotros los resultados de sus estudios doctorales, postdoctorales o de resultados de los proyectos de investigación en los que están o estuvieron involucrados. Queremos agradecer profundamente. We want to deeply thanks to Raquel Granados Aguilar from Costa Rica, but living in the United States. Joao Paulo Soares de Cortés and Renata Jordan Enríquez de Brasil. A Ignacio Ibarra Cofré de Chile, aunque viviendo en el Reino Unido y trabajando en Reino Unido. Y también a Mariana Correas González y a Damián Groch, ambos de Argentina. A todos les agradecemos ser parte de esta actividad. We are very thankful to all of them to accept to be part of this activity.
Teremos, então, 6 profissionais em geomorfologia dos países Costa Rica, Brasil, Chile e Argentina, alguns destes vivendo e trabalhando fora da América Latina, que vão compartilhar com a gente os resultados de suas pesquisas. Gostaríamos de agradecer, então, a Raquel Granados Aguilar, da Costa Rica, João Paulo Soares de Cortés e Renata Jordan Henriques, do Brasil, Ignacio Barra Cofré, do Chile, Mariana Correas Gonzalez e Damián Groch, da Argentina, por terem aceitado esse convite para fazer a apresentação de seus trabalhos hoje aqui. Muito obrigada.
We hope the dissemination of the results of their work will motivate other young researchers, students, and professionals to discover the remaining questions about landforms and processes of the Earth's surface and their interaction with the atmosphere, lithosphere, and biosphere, as well as with the society and its infrastructure. Also, we hope to reach the IAG intention to promote this type of meetings, useful to know each other's, and to strengthen geomorphology in our continent. Esperamos que la difusión de los trabajos de nuestros disertantes sea una fuerte motivación para otros jóvenes estudiantes, investigadores, jóvenes profesionales, para descubrir los interrogantes que aún se nos presentan cuando estudiamos o cuando nos plantamos frente a geoformas y procesos que modelan o que han modelado la superficie de nuestro planeta. Cuando nos interrogamos acerca de sus interacciones con la atmósfera, con la litosfera, con la biosfera y con la sociedad que sobre ellos habita y sobre la que implanta su infraestructura. Asimismo, también es intención de la IAG que estos encuentros sirvan para reunirnos anualmente, para conocernos, para fortalecer el desarrollo de nuestra disciplina en nuestro continente americano.
Esperamos que a divulgação dos resultados dessas pesquisas possam servir como motivação para jovens pesquisadoras e pesquisadores, estudantes e profissionais para buscar as questões associadas às geoformas e aos processos que têm modelado a superfície de nosso planeta, assim como suas interações com a atmosfera, litosfera, biosfera, com a sociedade e o espaço produzido. Assim, esperamos que essa proposta do IAG possa acontecer anualmente para que possamos conhecer e fortalecer o desenvolvimento da geomorfologia em nosso continente.
Okay, no more words. It's time to start with our first presentation, ¿no? Ya es momento de presentar a nuestra primera disertante.
Sem mais palavras, a gente passa então para as apresentações. Por favor, André.
Ella es Raquel Granados Aguilar. She's geology from the University of Costa Rica, and also she got her PhD in geology in the Texas A&M University, where is at present is the coordinator of the program of water management and hydrological science interdisciplinary program there in that university. She's a postdoctoral research associate and also graduate assistant for teaching and research in that university. She will present us her results about the electromagnetic induction to model the internal structures hydrological flow connections in the upper Camp Bird Rock Glacier in San Juan Mountains en Colorado State, the United States. Su trabajo se versa sobre la inducción electromagnética para el modelado de la estructura interna y flujo hidrológico del glaciar de roca Upper Camp Bird en San Juan, Colorado, en Estados Unidos. Raquel, te dejamos paso a vos para escuchar tu presentación.
Muchas gracias, Andrea y Grace, por la invitación. Thank you very much for the invitation. I'm honored to be here. Good afternoon to you all. It's morning for me, but good afternoon to you. I will be presenting a chapter of my PhD dissertation titled Using Electromagnetic Induction to Model the Internal Structural Hydrological Flow Connection of the Upper Camp Bird Rock Glacier in the San Juan Mountains. This was published last year in the journal Geomorphology. Okay, so what are the take-home points? Basically, what I want you to remember is that the Upper Camp Bird Rock Glacier has an internal structure that consists of 3 zones. We have a debris cover, an open matrix of frozen components, and a meltwater component. I also would like you to remember that after using 2 electromagnetic induction systems, we conclude that the time domain method resolves small-scale heterogeneities in this environment and allows us to reach great depths. We also discovered the limitations of the frequency domain system in this environment, where there are big conductivity contrasts and the EMI signal is impacted by anthropogenic structures. The purpose of this study was to characterize the hydrological importance of a rock glacier in the periglacial critical zone using non-invasive methodology, as well as to assess the applicability of those 2 geophysical instruments in a highly heterogeneous landform. So what is the research question, right? As I just mentioned, can we use non-invasive methods to map the subsurface characteristics of rock glaciers? I'm going to talk a little bit about this while you watch this brief drone video so you can have an idea of what this particular rock glacier looks like from the air. Basically, we're interested in rock glaciers because they function as alpine aquifers, and they have a debris cover that serves as a blanket and insulates the internal ice from direct solar radiation, which prevents rapid melting. This is important as water resource availability is increasingly threatened, particularly in environments that we know are highly sensitive to changing climatic conditions, such as the periglacial environment. So again, this leads us to the problem question, can we use these methods? So what really interested us about this and rock glaciers in general? Well, rock glaciers have a wide distribution and are one of 3 sources of water in periglacial environments. These are glaciers, aquifers, and rock glaciers. As you may know, rock glaciers consist of unconsolidated, poorly sorted rock debris shell, which is supported by internal ice. The frozen core of the rock glacier allows for plastic deformation, and rock glaciers exhibit movement downslope. In this drone image, we can see the lower portion of the Upper Camp Bird Rock Glacier and the toe over here. So I also want you to know the characteristic superficial features, and over here you will note some mine tailings. Now, rock glaciers and permafrost. So in periglacial regions, permafrost can occur in different forms. We can have permafrost in steep head walls, rock glacier forms, and glacial tills and soils. The permafrost distribution in these areas is going to depend on topography, snowfall aspect, and mean annual ground and air temperatures. Permafrost is mostly discontinuous to sporadic and alpine watersheds. And it's important to note too that north-facing slopes in the northern hemisphere receive less sunlight. Thus, this is going to favor the accretion of mountain permafrost. Now, what we have here is a conceptual model of the hydrology of a rock glacier that was developed by Giardino, my professor, and others. Thanks to this and other works by them, we know that rock glaciers are a cascading system that is responsible for much of the fluid mass transfer in alpine aquifers. In this diagram, we can see the hydrological inputs entering the subsystems, going through phase changes. We see they follow different pathways through the rock glacier, and part of those inputs are going to remain in storage for varying periods of time, and part of them are going to exit to subsequent subsystems in the form or in the form of outputs. Now, what is this study area? So it's in the state of Colorado, as outlined here in gray, specifically in the San Juan Mountains, which are part of the Rockies. So here you see outlined in purple the Uncompahgre River Basin, which extends over 7 counties in southwestern Colorado and includes this basin that's called the Imogene Creek Basin. The rock glacier of our interest is the Upper Camp Bird Rock Glacier, which is located in the headwaters of Imogene Basin. So we're zooming into it right now. Now, one of the most productive mines in this area, so the closest towns are Ouray and Telluride. One of the most productive mines was the Camp Bird mine, which was producing gold, silver, lead, copper, and zinc from the 1890s until the early 2000s. So one aspect that I want you to note and keep in mind is that in terms of anthropogenic influences, there has been extensive mining underneath and into the rock glacier from the 3rd level of this Upper Camp Bird mine. And that's why we call this rock glacier the Upper Camp Bird Rock Glacier. Now, how do we do this? How do we use non-invasive methods to characterize this rock glacier? Well, we do field work, of course, complemented using drone and satellite imagery to determine superficial characteristics. And we also use near-surface geophysics, particularly 2 types of controlled source electromagnetic induction systems to determine the internal makeup of the rock glacier. So here what we have is a satellite image of the Upper Camp Bird Rock Glacier, where you can see the erosion zone or the source of debris, which is directly connected to the depositional zone or the main body of the rock glacier. And I want you to note the direction of flow and also that this is a north-facing slope. Now, if we look at the these drone images, we can see that this rock glacier has very well developed microrelief. We have bridges, we have furrows, and we can see a clearly differentiated toe slope. So this indicates this is an active rock glacier. We can also see in this map, and as you can tell, I flipped the image so that you can see the rock glacier from the toe looking up to the head wall. We can see the steep slopes that are supplying the debris to the rock glacier. Now we look at the aspect in Imogene Basin. We see that it's mostly north, northwest, northeast, but more importantly, the head of the rock glacier is located on a north-facing slope, which means the rock glacier is receiving less direct sunlight. And like I mentioned before, this is going to be good for permafrost accretion. Now, what have we learned about the Upper Camp Bird Rock Glacier? And we can see here that the length is greater than the width, which is characteristic of what we call tongue-shaped rock glaciers. And this particular rock glacier covers an area of about 167,000 square meters. The height is informed by subsurface information, so this can be thought of as the depth to the bedrock. This corresponds to a volume of over 13 million cubic meters. Based on work with other rock glaciers, we estimate the volume of ice in the Upper Camp Bird Rock Glacier to range from 40 to 60% of the total volume. so between 5 and 8 million cubic meters. Now let's look into the methodology. We used a frequency domain system that's normally or commonly known as the EMI profiler or EMP400. This is a great system in terms of how easy it is to operate. Typically, you will have one operator. In this case, because of the rough terrain, we had to have 2 people operating, one holding the equipment and the other operating or sending the signals. And basically, you would use this type of system when you want to cover or profile large areas in a relatively short amount of time. So it's usually employed to obtain data that doesn't necessarily penetrate much in the subsurface. So it's typically operated at 3 different frequencies, and you are going to get high resolution, but not in depth. Now, the other system that we used is called the GTEM by Geonics. This is a time domain electromagnetic induction system. It basically works by shutting off a current that you're inducing, and as the time passes, the secondary currents will diffuse away from the transmitter, reaching greater depths and propagating outwards. So this is going to allow you to reach much greater depths, and it also is set to produce a realistic data collection because the type of model that it uses, it's a layered Earth model. So it allows you to, instead of assuming a homogeneous environment, it allows you to have a more realistic representation of the subsurface. So with this system, you can achieve detailed and stable data collection, and it has capabilities to perform one-dimensional inversion of the data on site. For this particular study, we used the GTEM on in a central loop configuration as shown here. Now, the data collection design for this rock glacier, it consisted of 7 lines with 5 stations per line. You will notice that we have concentrated all the stations in like the midsection and somewhat close to the toe. This is because as you get closer to the head wall, the slope increases significantly, and the terrain gets rougher, and it's very complicated to set up the equipment. And so for each of those lines, we will use both equipments, right? So the spacing between the GTEM stations, so the time domain system, is 25 meters, whereas the lines are 50 meters apart from each other, except for lines 7 and 6, which, as you can see here, are only 40 meters apart. Now, each profiler line, so when we use the frequency domain system, the way we used it, it's going to continuously record data. So each of those lines is going to represent 30 discrete measurements that are 5 meters apart. Now, what does the data look like? So for the EMI, or the frequency domain system, you can plot the data line by line, just using Excel or some other software. But you can also use more specialized software to interpolate the data and produce a 2D surface showing the distribution of the apparent conductivity. And I'm hoping you're noticing that there might be something wrong here, because all of the apparent conductivity data is a negative, and we will get back to that in a second. Now, for the GTEM data, like I said, the system allows you to do a 1D, one-dimensional inversion, so you end up with depth versus resistivity profiles of of the measurements, right? So basically, what you can do is you can either fit the data manually. So that's what we actually ended up doing. So you can see an example here. So the fitted model that was manually adjusted versus an automatic model inversion generated by the software. So you can see that we had to fit it manually so that it would adjust to the data better. Now, the effective penetration that we reached using this system was 96 meters. Okay, so what does it all mean? Now, I told you to keep in mind those strange numbers, right? Apparent conductivity numbers are negative. So we think that the EMI profiler was very susceptible to environmental noise and lateral conductivity contrasts, which produced undesirable results, right? The negative apparent conductivity values obtained here were likely a result from site disturbances related to historic mining activities. So we mapped some of the mine tunnels that go through the rock glacier, and you can see how it seems like the signal is being affected by that. Additionally, we found mine carts and other remnants buried close to the surface of the rock glacier. So this could also affect the measurements. Now, for the GTEM data, we use, you'll find different charts like this. So where you can see ranges of electrical resistivity values that are expected in near surface geophysical investigations. And you'll see that there is a lot of overlap between the expected resistivity of most subsurface materials. So of course, your interpretations are going to be driven by local geological information. And so if you remember, we had the uninterpreted version of the models earlier. And this is what our interpretation of what is going on at the Upper Camp Bird Rock Glacier looks like. So we can see each of the stations, we have an interpretation for each of the stations and each of the lines. So you can see the distribution. I know it's a lot of information to put in one slide, and I apologize about that, but it's just to give you an idea. So we have certain resistivity ranges that we're interpreting as volcanic rocks. Then we have what we're calling the thawing zone. So this is an area where you might expect some liquid water. And then we have what we're calling the permafrost, or the frozen components of this rock glacier. And this is going to be, of course, where you have a mixture of sediment, rock, ice, and you might even get a little bit of melt water component, but mostly we're seeing a separation. And then there are areas where we see different resistivity ranges that are pretty, are significantly different from the others. And we think this has to do with the hydrothermally altered rocks. And we have mapped, or we didn't, but there are mapped hydrothermal altered rocks in the area. So it fits with the model. So with all this information, we can somewhat put together a conceptual model for water flow through a rock glacier, or through this one in particular. So we know that rock glaciers have a very heterogeneous interior makeup, right? So this is going to complicate the hydrology, of course. We have varying grain sizes and ice contents, which in turn are going to result in varying porosity, permeability, and interconnectivity, which is going to make it really hard to define the pathways for water flow. So this model for water flow through a rock glacier was by Giardino and others. And it explains what we think we're seeing here at the Upper Camp Bird Rock Glacier. So we have the active layer that we see up here. which consists of the volcanic debris, the volcanic rocks, the debris cover. Then we also will have the flowing zone that we encountered above the permafrost layer within this area. So you will have kind of like pockets of water here and there, but you will also have water flowing through. The internal variations in the ice sediment ratio within the permafrost layer are likely responsible for the different resistivity ranges that we recorded within that same layer. We also have thawing zones that are beneath this ice-rich layer, and we think these could correspond with the what some people call the subpermafrost flow, or other people refer to this as a deep subsurface aquifer underneath the ice-rich layer. Thanks to the great depth penetration that we were able to achieve with this equipment, we can see the volcanic bedrock at the bottom of most soundings. So we think we're getting a pretty good idea of what the internal makeup of this rock glacier is. So what can we say about all this? So local conditions at the Imogene Basin, such as elevation, weather, slope, and aspect, favor the preservation of permafrost. The upper Camp Bird Rock Glacier is connected to the debris source, which is going to favor further ice preservation by maintaining a thick insulating debris cover. The use of non-invasive methods allowed us to come up with a very detailed interpretation of the surface characteristics by using drone and satellite imagery, as well as of the internal composition and hydrology of the rock glacier using near-surface geophysics. So we know that this tongue-shaped rock glacier is active and is characterized by a highly heterogeneous internal structure. So going back to the main points, the upper Camp Bird Rock Glacier's internal structure consists of 3 zones. We have a debris cover, an open matrix of frozen components, and meltwater component. We know that the EMI, or the time domain electromagnetic induction system, resolves, the frequency domain electromagnetic induction system is very sensitive to environmental noise, and underground structures are going to impact the signal, whereas for the time domain electromagnetic induction system, or the GTEM system that we used, this is going to average the heterogeneities, and it's going to deliver promising results, allowing us to obtain deep penetration depths. So that's what I had today. Thank you very much for your attention. And if you have any questions or comments, please do let me know.
Thank you, Raquel. Congratulations for your work. It's very impressive, very interesting. I'm looking into the chat. There is a question, or yes, from Mariana. Thanks, Raquel, for your great work presentation. Could you explain, please, how did you estimate water content of the glacier? I mean, how did you disaggregate water from debris? Thanks.
Okay. Thank you. So basically, we estimated, I can go back to that slide. We estimated the ice content generally, because it is a bit, I want to say easier. It's a bit easier to estimate the ice content rather than the water content. But again, these are just estimates. We have the data where it can show us the depth, and to some extent we can extrapolate that and have a good representation of the distribution of ice and water. However, the estimates are just based on, like I said, like we think 40 to 60% of the volume of the rock glacier will correspond with ice or with water, whether it is in solid or liquid form. So it's just a very generalized estimate. Of course, you know, we're trying to focus on non-invasive methods, but of course, you know, there's a need for ground truthing, and it would be much easier if we could have some preparations to actually ground truth that data, and then more accurately describe how much water we think is stored in this particular rock glacier. But I will take this opportunity, now that you posed this question, to say that the importance of rock glaciers in terms of hydrology and water resources, it's really at a basin or watershed level, not as an individual landform. So we've encountered people thinking, well, you know, if we run out of water, can we go and use that rock glacier as a source of water? And that's not necessarily what we're saying. What we're saying is that it's important to preserve rock glaciers. I know that in some areas, well, here, for example, it was mined for a while, and luckily they stopped mining it, which is helping us preserve that resource. But in all other areas, rock glaciers are mined even for construction materials, maybe not necessarily the gold and silver and all the precious minerals that we had here, but even for you know, borrowing for construction. And so I think it's very important to raise awareness about the importance of these landforms at a watershed scale, because they maintain the flow of water in a lot of these alpine creeks through the summer. And so the combined discharge of all of these rock glaciers within a basin is going to really maintain the flow in these alpine areas. So I hope I answered your question.
Thank you, Raquel. There is another question from Sebastián Vivero. He says, thank you for your interesting presentation. And he asked, which is the average superficial movement of the glacier? Can you identify different zones of movement, slow, medium, fast?
Yes. So I personally didn't work on estimating the rates of movement of this rock glacier, but other people have. And they've identified, I can share that information too. They've identified areas in which there is no movement, because there are areas where the rock glacier is actually not active. And so you can see this with micro relief. You can see the way it kind of forms folds on the surface, where the areas that are actually moving versus areas that are not. And there are definitely areas where it moves slower than others. And we think this is due to, you know, phase changes and like very complex interactions that are happening within the rock glacier. I think the estimated average rate of movement for this rock glacier in that middle zone, kind of like where we concentrate on most of our soundings, it's about 70 feet per year. So it moves very slowly, which is
okay.
Good.
Thank you, Raquel, and thank you all the audience that listen. Very interesting to your presentation. Okay,
thank you.
This time we are on time to pass the torch to our next presenter.